For generations, we believed our solar system ended with Neptune, then Pluto was discovered. But even Pluto's orbit couldn't explain certain gravitational oddities at the edge of our system. Whispers from the cosmic frontier suggested something else, something massive, hidden, and far beyond the reach of ordinary telescopes. Astronomers called it Planet 9, a mysterious world that might be lurking in the darkness, or possibly, something even more exotic. Today, we explore how cutting-edge technologies, quantum AI and the James Webb Space Telescope, are uncovering clues that could change our understanding of the universe. The idea of unseen planets isn't new. In the 1800s, astronomers noticed that Uranus wasn't moving exactly as predicted. These anomalies led to the discovery of Neptune. Later, similar irregularities hinted at a further object. What was eventually found was Pluto. But Pluto, as it turned out, was far too small to cause the observed gravitational tug on Uranus and Neptune. For decades, this mystery was largely forgotten, until strange movements in the Kuiper belt reignited the search. In the early 2000s, scientists studying the outer solar system noticed something odd. Several icy bodies, known as trans-Neptunian objects, TNOs, were orbiting in highly unusual, clustered paths. These objects, far beyond Pluto, should have had random orbits. Instead, they seemed to be aligned, as if something large and invisible was tugging them into place. The probability of this being a coincidence was less than 0.01%. Something massive was out there. In 2016, astronomers Konstantin Batygin and Mike Brown proposed a bold hypothesis. There could be a ninth planet, 5 to 10 times the mass of Earth, orbiting far beyond Neptune, possibly taking up to 20,000 years to complete a single trip around the Sun. This theoretical world was dubbed Planet 9. But there was a problem. We couldn't see it. Even with powerful telescopes, no direct observation confirmed its presence. It was either too far, too cold, or hidden in the glare of the galactic plane. The mystery deepened. That's when the search entered a new era, one powered by quantum artificial intelligence. Unlike traditional AI, quantum AI uses principles of quantum mechanics to process vast probabilities, enabling it to sift through enormous astronomical datasets at speeds unattainable by classical systems. Scientists fed it everything: decades of infrared sky scans, orbital models, TNO data, and deep space thermal maps. After millions of simulations, the AI pinpointed the most probable sky regions where Planet 9 might be found. Now, all eyes turned to the James Webb Space Telescope, the most advanced observatory humanity has ever built. Unlike previous telescopes, JWST could peer into the coldest, darkest parts of the sky using its powerful infrared sensors. It could detect faint heat signatures and reveal celestial bodies billions of times dimmer than visible stars. Using the coordinates refined by quantum AI, JWST scanned the targeted zones. And there, faint, slow-moving, and barely detectable, something appeared. JWST had spotted a cold object drifting across multiple frames. It wasn't a background star or a known TNO. Its motion and estimated mass suggested it could be exactly what astronomers had long theorized: a planet 5 to 7 times Earth's mass, orbiting at the edge of the solar system. But then came a twist. As scientists zeroed in on the possible location of Planet 9, an unexpected and radical theory began to gain traction. What if this elusive object wasn't a planet at all? What if it was something far more exotic and ancient? Some physicists proposed that Planet 9 could, in fact, be a primordial black hole, a theoretical object born in the chaotic moments just after the Big Bang. Unlike stellar mass black holes, which are formed from the collapse of massive stars, primordial black holes could have emerged from extreme density fluctuations in the infant universe. These tiny but incredibly massive entities could have the mass of several Earths, yet be no larger than a grapefruit, rendering them virtually impossible to detect using traditional telescopes. Such an object would be invisible to visible and infrared light. It would emit no radiation and reflect none. It would pass undetected through the cosmos, revealing itself only by its gravitational influence on nearby bodies. This possibility was both thrilling and terrifying. It meant that our solar system could be harboring a black hole, not far beyond Pluto, tugging silently on everything around it. The patterns observed in the orbits of distant Kuiper belt objects matched what one would expect if such a compact and dense object were hiding in the outer solar system. Quantum AI struggled to distinguish between the gravitational pull of a dense planet and that of a black hole. Both could explain the same orbital anomalies. However, in one specific region of the sky identified by the AI, the James Webb Space Telescope, JWST, noticed something extraordinary, an extremely faint, short-lived spike in infrared radiation. This wasn't a random occurrence, it happened more than once, and always in the same region. While the signature was subtle, it was consistent with theoretical predictions. A micro-black hole occasionally interacting with interstellar dust or dark matter particles might emit tiny bursts of radiation detectable in the infrared spectrum. The implications of this were staggering. Had JWST just captured the first direct signal of a primordial black hole, a leftover fragment from the birth of the universe? If confirmed, this would not only revolutionize our understanding of the outer solar system, but also open a window into the early universe's structure, dark matter physics, and even the geometry of spacetime. Scientists across the globe were stunned. Research teams scrambled to analyze the data. Within days, papers began pouring in from cosmologists, particle physicists, and planetary scientists. Debate intensified. Some argued it was a planet shrouded in a dust cloud. Others leaned into the black hole theory, suggesting that this might finally be the missing link connecting observable gravity to the unseen realm of dark matter. If this object turns out to be a true planet, a rocky or icy world orbiting billions of kilometers from the Sun, it would still be a remarkable discovery. Such a find would force a rewrite of planetary formation theories. How could such a massive body form so far from the Sun? Did it migrate there over billions of years, or was it captured from interstellar space? Its existence would mean our understanding of the solar system's boundaries was dramatically incomplete. But if this object is a black hole, especially a primordial one, the implications could be even more profound. It would mean that dark matter, which makes up 85% of the universe's mass, might be composed, at least in part, of these ancient black holes. It would give physicists a direct object of study, something tangible that links general relativity with quantum mechanics. And more intriguingly, it could suggest that black holes are far more common than we ever imagined, hiding in the shadows of galaxies, undetected but influencing everything. What's certain is this: something massive and mysterious exists beyond Neptune. It bends the paths of comets, shapes the orbits of distant icy bodies, and hides from every form of